Now, Lenz's law is a statement of conservation of energy. When you are generating electricity, for example, when you push the bar magnet here into the solenoid, we know that the solenoid will be cutting the flux, so there will be EMF induced. That means there will be electricity being generated. So we cannot produce electrical energy out of thin air. We have to convert some energy into electrical energy. So Lenz's law tells you how that is made possible. For example, if I were to push the bar magnet into the solenoid, so when the coil cuts through the magnetic flux, there are two possible ways that the current can flow. One is it flows this way or the other way. Right? As you can see, there are two possible ways. So why is this incorrect and why is this correct? The reason is very simple. If the current flows in the coil this way, then we will be able to find out the direction of the magnetic field of your solenoid. So the magnetic field of a solenoid, remember we use the right hand grip rule, where the fingers represent the current and the thumb represents the field. So if you put your fingers turning, like use your right hand grip rule, you will notice that this side is south and this side is north. Okay? So what will happen is, as you are pushing this magnet into the solenoid, this end pole of the magnet will be attracted to the S pole of the solenoid, so they will attract each other. And if they attract each other, do you need to push in anymore? You don't have to. You can let go. It will move by itself, so the CAIE increases. It cuts the flux faster, so the electrical energy increases. But where does this additional energy come from? Can you see it doesn't make sense? There's no conservation of energy, so this is wrong. But if, when you push the bar magnet, the current flows the other way, if we use our right hand grip rule, we will notice that this is north and this is south now. So therefore, as we are pushing the bar magnet into the solenoid, the end pole of the bar magnet will be repelled by the end pole of the solenoid. So that forces you to do work against the repulsion. So as you keep pushing it in, you keep doing work against the repulsion, and that work that you do can be converted into electrical energy. So therefore, the current must flow this way and not this way. So there's only one way to determine how the current flows, which is what I just explained to you. Alright, there's no other way for a solenoid. But if it's a straight current carrying conductor, then we can use Fleming's right hand rule, which I'll show you in the next slide. Now, if let's say we have another example where we have this bar magnet and you have this wire that you push down. If the wire is being pushed down, can you see it will cut through this magnetic flux? So as it cuts through the magnetic flux, there will be EMF induced in the wire, which can either cause current to flow this way or this way. But this way is labeled incorrect, this way is labeled correct. So why? So once again, it is a statement of conservation of energy. So let's look at why this is wrong. Now imagine when you push the wire downwards and the current starts to flow here. Now when the current flows in a conductor, it will actually cause the conductor to generate a magnetic field. Remember when the wire carries a current, it generates a magnetic field using what? Our right hand grip rule, right? We can find out. So anyway, so if there's a magnetic field exerted by or caused by the wire and it interacts with this magnetic field, there will be a force. So what is the direction of the electromagnetic force? This one we use the Fleming's left hand rule. So if you take out your Fleming's left hand rule, the field points this way, that means points this way, and current points this way, you will notice that the force is also downwards. Okay, so you need to imagine this So maybe I draw So like this, like this. This is how my thumb looks like So this is my pointer. This is the middle finger, and this is the thumb. Okay, so can you see the force is downwards? Okay, so if the force is downwards, That means I no longer need to exert any force to push the wire down. It will move by itself because the electromagnetic force is downwards. So as it pushes the wire down, KE increases, then it cuts the flux faster, the electrical energy also increases, but nobody does any work. So again, it is wrong. But if the current flows the other way, so now it will look like this. I got how many fingers? 2 left, right? Okay. Okay, so this is my thumb. This is the pointer. And this is the middle. Can you see that now the force is upwards? So if the force is upwards, that means as I'm pushing the wire down, I have to do work to overcome the force. So then my work done can be converted into electrical energy. Now there's a shortcut. Because this is a wire, we can use a Fleming's right-hand rule. So Fleming's right-hand rule, so the difference between Fleming's left-hand rule and right-hand rule, there's a small difference. Now, the pointer fingers still represent magnetic field. That doesn't change. But the other two is different already. The middle finger, for a Fleming's left-hand rule, represents the direction of the current that you supply, right? But in Fleming's right-hand rule, the middle finger represents the induced current. Okay, but it's also current, but it's induced current. Now the thumb is the biggest difference. In Fleming's left-hand rule, the thumb represents the electromagnetic force, but in Fleming's right-hand rule, it doesn't represent electromagnetic force. It represents direction of motion of conductor. So what I mean by direction of motion of conductor? So I'm trying to draw. Only thing is, when I show out my right hand, I cannot wrap my left hand. Okay. So try to imagine. This is my pointer finger. This is my middle finger. Wait, and this is my thumb. Does it look correct? No. Something weird. Like this. Then it looks better. Okay. So this is my pointer finger.
That's the middle, is it? Then the thumb.
This is the middle. And this is my thumb. Okay. Okay, anyway, so that is how you use a Fleming's left-hand rule. So the field is pointing pointer finger, then the thumb points down, and then you get the current downwards. I mean not downwards, as in current this way. So field this way, so that's my pointer finger. Thumb goes downwards because that's the direction of motion of conductor, and then you get the current here, induced current. Huh? Oh, you know what I just thought of or not? Wait, I got an idea. So, or you can use this alternative So, can you see the pointer finger here is this way? The current here, induced current, because the motion is downwards. Okay, so that's how you get it So I repeat, so this is direction of the field. This is a pointer finger here. This way, Can you see the field going out? So this is the pointer. Then the thumb points down because the motion of this conductor is downwards. So then the induced current is here.
So this one is to find the induced current?
Yeah, this is to find the direction of induced current. If you know the field and you know the direction of motion, then you straight away can find the direction of the induced current. Now there's another example of Lenz's law. For example, if let's say this is a solenoid, so this is a symbol for a solenoid, and we connect the solenoid to a CRO Okay, this is your CRO screen.
So what are you drawing? It's not appearing.
Oh. Okay, then what happens is, let's say you drop a bar magnet, okay, through the solenoid. So as the bar magnet falls through the solenoid, it will induce an EMF on your CRO, right? Not? Because the CRO will show you a trace something like this. So I just imagine like this. Like this and then like this. So first thing you will realize is that the peak for the first part is lower than the peak for the second part. Magnitude wise, amplitude, this is smaller, this is bigger, right? Not? Then you will notice that this is positive, this is negative. Then you realize that the time here longer, time here shorter a bit. So why all this happens? So let's first talk about why positive and negative. You see, when it first falls, right, there'll be cutting of flux here, right? So if there's cutting of flux here, there'll be an EMF induced in your coil, which will try to oppose the flux change. So how does it oppose? If this side is N pole, then this side of the solenoid must be N or S to try to prevent it from coming in. This must be N. So if this side is N, this side must be S. So, but when the solenoid, when the bar magnet leaves, okay, when the bar magnet leaves the solenoid, so you will notice that again, as this bar magnet tries to leave, this part still cutting the flux, right? So there will be an EMF induced. And according to Lenz's law, the current that flows here will try to oppose the change that causes it. So when this is trying to leave, it will try to prevent it from leaving. So the S goes out. So this side must be N or S to try to prevent it from leaving. So this will switch to N. So the top part here will then switch to S. So can you see the polarity switches? So that explains why the EMF switches direction, because the current is actually switching direction. It means originally maybe the current flows this way, now it flows the other way. Because the polarity of the solenoid has to reverse. Right. So why is this peak lower than this peak? It's because when the bar magnet is falling initially, this part is slower, so it cuts the flux slower. This part will cut faster because of gravity, will cause it to fall faster and faster, so this part will cut faster. So this part cut faster, so the induced EMF is higher. And that also explains why the time taken for the first half is actually longer than the time taken for the second half. So let's say we have another case here. Let's say you have a cell connected to a rheostat and then connected to a a solenoid. So let's draw the solenoid this way. Okay, so it looks a bit weird. So, and then you have another solenoid facing it, but this solenoid is actually joined to a different different circuit. So they have another circuit here. Let's put a resistor here. So this is another solenoid. So if you see from the 3D view, it looks like this. But if you see from the front view, this will be your first solenoid. And this one will be your second solenoid. You understand? So they are facing each other just like that. Okay? Easier to imagine that way. So what will happen is, let's say the current is already flowing this way. You see that? So it flows from the back to the front. So this to imagine a bit from the back to the front. And what happens is, let's say I reduce the resistance here. Alright, this resistance, I reduce it. So what happens to the current in your solenoid? Your current will increase or decrease? The current will increase. So the thing is, when the current increases, wouldn't this flux be stronger now? So the flux exerted here will be stronger. So as it grows, right, the solenoid here experiences the growth in flux. So therefore, it will have an EMF induced here because there's a change in flux linkage here. So which way will the current flow? That's my question. Will it flow from X to Y to Z and then to W? Or will it flow from W, Z to Y to X Okay, so which way will it flow? So because the magnetic field, let's figure out the magnetic field. If the current flows from back to front, so if we use our right hand grip rule, this will be north, this will be south. Correct? You try and see. Current flows from the back to the front. So that's your fingers. So your thumb will point to your right. So therefore, this is north, this is south lah. So because the current increases, the flux here will increase. That means this will get more and more north. Correct or not? Now, the EMF induced in this second solenoid will cause a current to flow. When the current flows, it will produce an effect to oppose this growth in flux. That means it's trying to get more and more north. So this side must be what? To prevent it from becoming more and more north. This side must be north or south to prevent it from becoming more and more north. It must also be north. And this must be south. So if we use our right hand grip rule for this solenoid now, so you use our thumb and point to your left. So your thumb points to your left, you will notice that the current flows from W to Z to Y to X. But if we reverse this, let's say now we increase the resistance so that the current decreases. Okay, so we increase the resistance so the current decreases. Then this side will get less and less north, right now. So if it gets less and less north, so this side must try to prevent it from dropping. So this side must be north or south. So this will switch to south and this will switch to north. So if it switches to south and north, then use your right hand grip rule. For this solenoid, you must point to the right, your thumb point to the right. So the current will now flow from X to Y to Z to W. That's how we use Lenz's law.
That's all for today's video. If you're interested in more genuine sharing by other geniuses, please subscribe to our channel and don't forget to turn on the notification bell, ding dong. Also, if you're struggling with one or two past year questions and the mark scheme just doesn't seem to help, Genie has got you covered. Feel free to let us know what question it is by filling in the Google form linked in the description below. GenieUs Hub will get genius teachers to fulfill your request for the solution. Genie will see you next time. Bye-bye.